Welcome everyone to the last day of this 5-day or 6-day workshop. We will conclude the event with a program manager panel, another social networking session, and reports from moderators. The moderators, Dr. Marconnet, Dr. Yee, and Dr. Vasu. The floor is yours.
All right. Good morning, everyone. So today is the last day of this exciting panel. And again, very happy New Year to everybody who's participating. Today we have the program managers panel. So myself, Subith Vasu, I'm an associate professor at the UCF. And Shannon Yee is an associate professor at Georgia Tech, and Amy Marconnet will be the moderators. We have slightly different format compared to your previous panels this week and in December. So we'll have introductions and opening remarks, which will be about 20 minutes. And we want the Q&A session to be more interactive. So we have prepared questions to these panelists ahead, and so we'll be going through them. And from the audience, we ask that you type your name and affiliation in the chat, and then we'll call you based on the order that you want to ask the question. So we want it to be more interactive, and so it's going to be more participation from the audience this time. So Shannon, carry on.
Great, thank you very much. So we're really excited to have this panel together today. Over the last week and back in December, you heard from many of these individuals. I'm just going to very quickly introduce our panel again. We have Dr. Michael Ohadi. Mike is currently a program director at ARPA-E. And he's on leave from his role as a professor in mechanical engineering from the University of Maryland. Next, we also have Sven Mume. Sven is a program manager with the Building Technologies Office at DOE. Prior to, I guess, joining the Building Technologies Office in 2012, Sven was at ARPA-E as a technology to market advisor, and he led the commercialization strategy for the MOVE program, which stands for Methane Opportunities for Vehicular Energy. Next, we also have Dr. Peter de Bach. Peter is currently a program director at ARPA-E, and his interests have been focused on electronic thermal management and aviation propulsion systems, like we heard about yesterday. Also on the panel, we have Dr. Matthew Bauer. Matt is a technology development manager with the Solar Energy Technologies Office at DOE. And he's been doing a lot of work recently on CSP for electricity generation and pump thermal energy storage, which we heard about yesterday. And last but not least, we have Dr. Ying Sun. She's a program director.
You lost voice.
So Shannon, we cannot hear you now.
So maybe I can take over since we lost Shannon. So he was finishing introducing Dr. Ying Sun, who's a program manager at NSF. And I think with that introduction, we can give the panelists their time to give a brief overview. So if the first panelist wants to take over, please go ahead.
Sure, let me wait for the slides to come up. Okay, great. Thank you, everyone. Good morning. Great to have the opportunity to be present in the last day of the workshop. Hope the next very brief 3 to 5 minutes I can share with you what would make a good ARPA-E proposal, and then my colleague Peter DeBach would follow with additional information after mine. Just a correction, as of a couple of weeks ago, I'm a program director emeritus and consultant as a special government employee, and helping to transition to Peter and other colleagues as I wind down my work at ARPA-E. Next slide. So I basically put the presentation together in terms of responding to the questions that Shannon had sent. Next slide. So ARPA-E is a new agency, barely more than 10 years old, as many of you might be familiar with. Next. So if you write a proposal for ARPA-E, you have to keep in mind that two things are very important to us: demonstrating that you are improving efficiency for energy conversion, and at the same time, you're reducing emissions. So if you propose a field that does not achieve these two, then we might say that, look, maybe this is an ONR type, or this is a DARPA type project, or another division of DOE, and this may not be ours. Next. So thinking of ARPA-E, think of a DARPA proposal. The ARPA-E was put together much like the format of DARPA, the way we handle the proposals and the way we select projects also likewise. All right, so a successful ARPA-E proposal would be the one that you can demonstrate impact, be it on energy efficiency, be it on CO2 footprint reduction, as well as the broader impact of creating jobs, reducing our dependence on imports for energy, transformative nature, bridging what would be a science idea of practical significance, and through the ARPA-E project, you will put that concept to practice and get some good stuff with it. And then I have yet to see good-sized proposals and successful proposals that are by one person or one university or one company. Usually, there are teams that bring different skills, different disciplines together to achieve the tasks and milestones of the project. Going on to next slide. So if you believe in the TRL system or what level of funding ARPA-E gets involved, I think we are at a level of TRL 1. And by the time you're done with an ARPA-E project, you might be at TRL 3 or 4. So the objective for us is to bring it to a level that somebody else can take it and commercialize the idea and take it away and create jobs with it. Going on to next slide. And following up with next. So there was a question as to what you can do in defining programs. I think you can play a significant role in two fronts. Number one is to come up with the idea, request a time with program director or somebody at ARPA-E. Typically, you start with the program director and run that idea by us. Typically, we ask a few minutes to share the idea, and then from there, it goes through months of us looking at the idea, evaluating it, analyzing it, and by the time it gets to the stage that we advertise it and FOA comes out, this may take 9 months to a year. Next. The other front that you can contribute is, in fact, through coming to ARPA-E and work in one of the three positions, either as a program director, what Peter DeBach and I are doing, or as a technology to market advisor, which Dr. Stephen Mummy was at ARPA-E before at that role, or come as a fellow if you're a fresh PhD graduate and would like to be exposed to many ideas. By being there, you can promote your field. If it's thermal management, for sure, you can play a substantial role. Next. Finally, we were asked to introduce one idea that is exciting, at least to the person that is proposing it, And I'll have a couple of ideas, but I would like to focus briefly on next heating and cooling of buildings. Next slide. I think Seven did a great job yesterday in terms of the works that BTO is doing in buildings. But I look at the typical air conditioning system, and it's basically nothing but a compressor, some piping, an evaporator, and a condenser. So we could discuss this whole field through a complete presentation, but basically that's what it is. A couple of heat exchangers, a compressor, and some piping. Compressor, a lot of research has gone to it, but the heat exchanger side and the packaging side can see substantial improvement. So if I look at opportunity here, this is not really, again, one entity, one opportunity. Definitely is multidisciplinary, definitely brings different ideas together. COVID has presented an excellent opportunity in terms of doing away with central air. We need to think about modular, that we can stack them up, bring them together, highly efficient. Size and weight can be substantially reduced. We can discuss how this can be done. Engaging appearance is very important, interactive, low noise. We have to substantially think differently and come up with concepts that are completely new. And finally, integrating heating, cooling, and hot water together could save you a lot of space and cost as well. And as Seven mentioned yesterday, of course, integrated thermal and electrical storage is pretty important. I think with that, I'm coming to my last slide. Next. All right, thank you.
Thank you, Mike. I'll take over from here. As Mike mentioned, I'm a new program director at ARPA-E. Many have known you from my prior roles, but I look forward to working with all of you in this new capacity. And my focus areas will be aviation hybrid propulsion and energy consumptions from electronics and electrical systems. I mentioned some of this yesterday, so this might be a repeat for some of you. So what are the next big challenges in the fields of thermal transport? And it really defines first what does the world need? What are the big needs? And understanding those trends is hard, and that's actually an area where I'd love thought leadership from experts like you. Approach an ARPA-E leader and say, hey, this field is moving this way. Those are the kind of things I'm researching myself, but I'd love to hear your thoughts on those as well. So we talked about different energy supplies yesterday. So energy storage, thermal or electrical are very important. Energy transport. Transportation is now the leading sector for emissions. So we need solutions there, as well as efficiency of new industry. So when we do get our highest exergy thing, which is electricity, let's use it very efficiently. And thermal technologies and thermal transport are essential for all of these. And to give you some examples, is here in this list of focus areas. When I look at transportation systems, think about moving megawatts, tens of megawatts of electricity on an aircraft. You might need to look at cryogenics or at advanced conductors. So these are transport problems. How do I transfer electrons from A to B, even if it's just 20 meters in an efficient way when you're limited by voltage and current? Low-cost cryogenic coolers could be a great improvement that we like to see, and technologies that could help with that. And in addition, when we do get propulsion energy, ARPA-E is currently interested in looking into ideas around propulsion technology. So if we do have shaft power, how do we get propulsion out of that? Efficiency of electrical systems. I just launched a webcast before the Christmas break on data centers. Kind of related to what Mike alluded to earlier. HVAC hasn't changed much in decades. And if you look at electronics typically running at higher than ambient, why do we need a heat pump to get the heat out? It's because the thermal resistance pad is sometimes inefficient. So ideas around that would be great to see as well. Superconducting compact cryocoolers are mentioned as well. And I think in addition, there's an opportunity for new fluids, such as supercritical fluids. I've seen a lot of research going on in the areas of high entropy alloys, material science using AI data. I'd love to see something similar for fluids as well. If I answer the questions that were posed by the panel, so what is unique about ARPA-E's funding programs? I think ARPA-E is an exciting organization, that exciting that I joined them because there's the ability to work on disruptive programs at the national level is extremely exciting. So the two main funding vehicles within ARPA-E are what we call open, and you can see the sequence 2009, 12, 15, 18, and an announcement, a link on the right. I hope everybody pens down. These are very large opportunities where we receive thousands of proposals and really look at what is unique, what addresses the ARPA-E objectives as mentioned by Mike before. Focus programs are a little bit more work where we actually then launch a particular area. Those require a little bit more work to set up, but that is another vehicle that ARPA-E uses. And how can PIs help? Help us understand your vision on the energy space, energy production, transportation efficiency, and share with us your vision for the futures, and let me know what are the things or widgets that need to be developed to have a transformational impact. Those are the discussions we'd love to have with you. And the greatest opportunities, I think there are many. New materials, additive ceramics, supercritical fluids, new fluids, materials to conduct better than copper, and also things as making technologies that already had a lot of research, such as two-phase cooling, perhaps more reliable and practical. That was my quick summary, and I'll pass it over to the next speaker.
Great. Next up, we have Sven Mume with the Building Technologies Office.
Great. Hold up, presentation. See it? Okay, great. So I manage both the building envelope as well as the thermal energy storage portfolios at BTO. I'll try and put on my PM hat here to try not to bias the presentation too much. So I'll be answering the same questions. So what is unique about your funding program? So first of all, BTO's mission is to is pretty pretty broad. So it goes from development, demonstration to adoption. So the whole spectrum. And so where do we sit? So we within Department of Energy, part of the energy efficiency and renewable energy division, we're part of the energy efficiency side of it. And so here in green, we're one of the technology offices, and we're an applied office. So we have a pretty big budget of $285 million in FY20. So if you look at how it's broken up, about half of it, roughly 140 million of that is in my area, in the emerging technologies area. Yet, what's unique about the overall office is that it spans R&D, integration, and deployment all the way to codes and standards. And that's pretty unique from all of the technology offices. So currently the program manager is Karma Sawyer of Emerging Technologies, but her last day is on Friday. So she asked me to step in here. So we'll see who that replacement is. So just a little bit more about emerging technologies. So we support high performance, energy efficient and flexible building technologies. So we've had some new thrust areas of flexible buildings are part of our grid interactive efficient buildings work, as well as we've also had a cross-cutting program based on advanced building construction, which really spans some of our sister programs on the integration side of commercial buildings and residential buildings. And we're really interested in pursuing areas that haven't been addressed by industry, similar to ARPA-E, but again, we're an applied office, so the TRL levels are a little higher. And we're looking to really look at new learning curves, again, similar to ARPA-E. So how can PIs help funding agencies better define trajectories? So I've looked at some ways to researchers be able to impact our work. And one big opportunity is to actively engage in our historically annual BTO peer review, where we review about 90% of our projects. And that's a really good time to change trajectories going forward, especially if you're willing to be a reviewer. So there's also an engagement in merit reviews of whether it's SBIR, FO, or our offices, typically annual FOA called the benefit FOA. If you're interested, we're actually seeking some reviewers right now. So for the SBIR FOA, we have, at least in my portfolio, we have 2 topics on low thermal insulation materials or thermal conductivity insulation materials and envelope diagnostics. And the benefit we have also thermal energy storage materials development projects and envelope topics. So again, if you'd be interested, please contact me. So we're also looking at having, we have workshops throughout. We're looking at actually having one in thermal energy storage in the coming months. We're also, there might be, we're working on a thermal energy storage consortium idea. So if that's of interest, please, reach out to me. And similarly, like ARPA-E has fellows, we also have AAAS and ORISE fellows. So we're always, looking for new talent. And that's a really great opportunity to really help shape, new thrust areas. So please let me know if you're interested in that. So what do we see as the greatest opportunities? This is a little bit biased since these are in my portfolio, but high R or low thermal conductivity insulation materials would make a significant impact in reducing energy consumption in buildings. Similarly, reducing energy consumption and adding grid flexibility with thermal storage, especially low cost, high performance storage, and looking at new approaches for managing heat and providing needed demand flexibility through different ways of managing heat versus just static insulation materials. Some other opportunities. Yeah, cool. These are some other opportunities with non-vapor conversion heat pumps, and I'll stop here.
Excellent. Thank you, Sven. Up next, we have Matt Bauer from the Solar Energy Technologies Office.
Hopefully everyone can see my screen without issue. Thank you for inviting me, Shannon, to participate. So I'll keep these remarks brief because I think there's a lot of overlap with the sister organizations at Buidings and ARPA-E with our program. So my name is Matthew. I work for the CSP program within the Solar Energy Technologies Office. So the lesser known of the 2 predominant solar technologies. Right here I have a nice graphic of what we call our Gen 3 program, which is one of the themes I'll briefly touch on today, about raising the temperature of thermal transport systems in order to create efficient and cost-effective systems. I showed this slide yesterday, so I'll touch on it very briefly. We are a cost-motivated office. We would like, if nothing else, to achieve cost parity with other dispatchable technologies on the grid in order to make a cost argument for a renewable energy future that is dependable, reliable, all those things. And with that in mind, we have a cost objective of getting to 5 cents per kilowatt as a levelized cost of electricity by the end of this decade. And our analysis shows that if we do that, we do see very significant deployment of CSP in the United States. But looking at that a bit more granularly, here's a waterfall chart of one path to get from present day technologies to that cost objective. And you can see on this waterfall chart, there's reducing the cost of the collector field, or the optical part of a CSP plant. There is reducing the cost of the power cycle, as well as increasing its efficiency. And we think those two levers will be turned by bringing the supercritical carbon dioxide Brayton cycle on board in the near future, which we're working aggressively for, as well as elevating the temperature compared to typical steam ranking cycles that CSP and nuclear plants operate with today. And then, of course, the last bucket is a bit of a catch-all for the middle third, the thermal transport system. But the major challenge there isn't just reducing the cost of those portions of the plant, it's increasing the temperature and keeping it reliable to enable a high efficiency power cycle. Zooming in slightly further, and I showed this slide yesterday, but what you do, and you can follow the logic here, you go from a cost goal, you go to how do I get to that cost goal, then what are some specific R&D techno-economic metrics I need for the system. I'll focus on maybe thermal energy storage, where we have an exergetic and energetic efficiency and a specific cost per kilowatt hour down here at the bottom with an outlet temperature. We have goals for our receiver, for our heat transfer fluid, which actually might not be a fluid, might very easily be solid particle media, as well as heat getting into and out of the power cycle and whatnot. And then on the right, you see a series of solicitations we've run over the last decade aimed at these goals. Some of the more recent ones, due to the way this administration operated, were very catch-all FOAs. So I'll break that down slightly on the following slides so you can get an idea of the type of work our office actually does. Actually, 2 slides later. One other point I'm going to emphasize, and this will get to one of the panel questions of what are some areas where the thermal transport community could help our office define roadmap trajectories, is while I have this specific idea of a path forward for electricity generation, the thermal industrial process heat or solar fuels market is a lot more disparate. It's a lot harder to pinpoint a solution point or solution space that describes it. And so it's open-ended. We've done a lot of work in desalination to date and solar thermal desalination, as well as somewhat in agricultural and food process heat. But one of the areas we're looking for in the future are some of these very high temperature potential markets, which might include solar thermal chemical production, solar thermal chemical fuels, as well as solar thermal chemical long-term energy storage. And those are areas we're actively road mapping and having conversations about what tools are in our tool belt, which I would hope that the scientific community can help show the robustness of certain phenomena that they've explored in the last years, that we can develop components and systems based off of. And the last bullet point here is thinking of high temperature mining and metals, which are probably well above 1,000 degrees Celsius, and like we'd like to do in a carbon neutral way. This slide became a click through. I know this is a bit of an eye chart, but I tried to put down in words in one spot some of the funding programs we've run recently so that you can get a feel for our programs. I'll start with these 2 that are in orange, which are our bigger scale demonstration programs. And our goal to get to large scale demonstration efforts is one of the unique factors of our programs. We start with early science efforts, we develop components, we exercise those components, and we put those components together to the pilot facility. We're really happy that we've recently made started negotiations with a team to develop a 5 megawatt SCO2 power cycle demonstration integrated with a solid media thermal energy storage company, Heliogen. It's coming online soon. You say, well, maybe that's might not quickly seem relevant to scientists doing research in laboratories, but I'll say an important aspect of that project is the integration with the scientists that develop the technologies that they're using are still active and alive at that point in the project. You see it as the inverse of programs like ARPA-E, who ask to have, business cases developed over the course of research projects. And the corollary of that is we still need research hand involved in high TRL efforts. The other program I'll note is that Gen 3 program, where we taking a few swings at ways to put together high temperature thermal transport systems. We look at moving particles at 800 C is one way to do this that are easily stored. It could be sand-like particles or others. We look at chloride salts at high temperature as another option. We've looked at liquid sodium, and we've looked at supercritical gases as another way to move and indirectly store heat at high temperatures. The programs in blue are different, kind of more of our standard solicitations that we look at, where we look for projects on the order of 2 to 3 million with a degree of teaming that can range academic, national lab, as well as businesses executing those. Touching on them briefly, we've looked at firm thermal energy storage, which I've talked about yesterday, open materials and manufacturing topics. We've looked at autonomous control systems and detection for heliostats. One of the process heat markets we've looked at closely is solar thermal desalination, and general advanced component development for CSP applications. And then lastly, I'll highlight some of our, one of our other modalities we use, the SIPS program, Small Innovative Projects in Solar. This is where we look to fund very open ideas for scientific innovations that could impact the CSP application, as well as we use a prize format, which is a unique way of letting, in a very open way, letting people come up and show that they have an idea that could work and work for the desalination application. And the other point I'll highlight is what we're talking about right now going forward. And probably the middle three bullets are the most interesting one to this community. We are looking very closely at next generation receivers. So for those of you not familiar, a receiver is the heat exchanger where concentrated light becomes thermal energy with the heat transfer fluid on the other side. But it's challenging at high temperatures, and we do think we'll have to move beyond even metal superalloys as an option for some of the materials. And it's a very challenging thermomechanical, potentially chemical, optical problem that it takes a lot of legs of science to stand up and really develop a bankable system. Building off of that, or am I out of time? Then I will flip to my last slide, which is just, as others have done, advertising that we have an open call for postdoctoral fellows and other fellows. And the deadline is, the first deadline is January 15th. So if you have anyone interested, please do apply. Thanks for the time, Shannon.
Great, thank you, Matt. And last but not least, we have Ying Sun with NSF.
Okay. Yes. Thank you. I just had some issue. Okay, so it's working. Yeah. Thank you, Shannon. Thank you, Amy, and Sudis. Really appreciate this opportunity, and thank you everyone for contributing. So I will go quickly over. Oh, I can share screen. Over the thermal transport process program at NSF. So many of you are pretty familiar with our program, but I will quickly go through. So we have a new, NSF has a new program director, Patranathan, started July of last year for his 6-year term. So NSF was founded by 1950, and the annual budget for last fiscal year was $8.3 billion. So we contribute a quarter of the federal funded basic research in US institutions. So NSF has 7 directorates. So I'm in the engineering directorate. And engineering directorate is currently led by Don Tilbury, and we have 5 divisions and 1 office. So I'm in the CBAG, Chemical Bioengineering Environmental Transport Systems, and for the thermal community, and if you're related to advanced manufacturing, it is under CMMI. If it's related to electronic photonic devices, it's under ECCS, and IAP funds as DTR, SBIR, as TTR programs, and also EEC, Engineering, Education, and Centers fund ERC, and also educational programs. And this is a special office. It's called EFMA. This is funding this new frontier in engineering, so EFRI topics. So this is our division. We have a total of 4 different clusters and 16 programs under this transport phenomena cluster, and that include combustion and fluid dynamic, particularly multi-phase process, and thermal transport processes. So the total budget is about $200 million, and 80% of that goes to the unsolicited proposals that you are familiar with, but there is a 20% of the funding goes to special programs. So now you may ask, what are the special programs? So one thing that is coming up is with a feasibility deadline is this, we work with International Space Station National Lab to look at transport phenomena research on the International Space Station to benefit life on Earth. This is a 6 years of that solicitation. And the specific interest of this fiscal year for thermal transport is to look at flow boiling and condensation fundamental side to use the NASA's flow boiling condensation experiment facility to benefit life on Earth. So with the feasibility form, deadline is actually will be next week. And the proposal deadline is March 2nd, 2021. So another kind of special program, this is foundation-wide initiative, is called the National AI Institute. This is a second year, and the second year we have 8 different themes. Engineering, I'm actually leading this theme 5, AI Institute and Dynamic System. So we had already the proposal in, but this type of initiative is a very important focus of NSF. This is a big program, a $20 million per institute program, and for $4 million per year for over 4 to 5 years. And it's to really build this advanced national and advanced foundational and user-inspired AI research and accelerate transformative and AI-powered innovation and grow this diverse, well-educated AI workforce and build nexus points between the universities, federal agencies, and industry partners. So here we have a list of industry partners and also the other government agencies that involved and participate in this AI Institute. Okay, so for this particular interest this year is AI Institute Dynamic System. We're specifically looking for real-time sensing, learning, and decision-making for engineering and science systems. So many of you are probably familiar with NSF 10 big ideas, and I mark, so there are actually 6 research ideas and 4 process ideas, and I mark those red ones are related to our thermal community. For example, the harnessing data revolution is very important, and also the quantum information science, and also navigating the Arctic, and the convergence research, and the diversity NSF includes, and mid-scale research infrastructure, and also NSF 2050. So please get involved in those interdisciplinary programs and collaborate with other researchers to actively engage in those activities. So in terms of this core program, thermal transport processes, it funds heat and mass transfer and thermodynamics. And so the focus that we have in recent years are basically 2 things. One is new metrology development, looking at in situ and high speed and non-invasive methods to accurately image or mapping thermal field. Right. So, and also we're looking into artificial intelligence, machine learning, and data science methodology to advance fundamental thermal science. So this slide kind of shows the active project in this program. What are the compositions? So, so we have 130 awards that we manage now, and the phase change is a big portion. Many of them are liquid vapor phase change, and the phonon transport nanoscale conduction is about 27%, and radiation about 11%, and convection is about single phase convection is about 8%. There are other less represented, for example, energy conversion and storage. We have been talking with DOE BTO office and trying to promote more new materials, new interface, and new understanding of energy storage, thermal energy storage, for example. And also then, you know, if you look at supercritical CO2 or other new materials, new system looking at thermal physical properties. And then the house, for example, we, because of the CARE Act, we actually have related to rapid COVID, we founded 7 projects of COVID-related rapid projects and other projects. So those are underrepresented, and I will be happy to see whether you have good ideas in those underrepresented topics. So I guess my time is up. So if you have any further questions, and you feel free to email me, and this is my email. Thank you.
Great, thank you so much, Ying. All right, so for the rest of this panel, I'm actually going to ask the panelists if they could unmute their microphone and camera. For the audience, if you have a question, please just type your name and affiliation in the chat window, and then we will call upon you to unmute your microphone and camera and ask the panelists your questions. So if there's any burning questions out there, please please type your name and affiliation in the chat window. But to kick us off, the moderators, we prepared a couple of questions. I'm going to quickly share my screen with the first question, which we have directed towards Ying and Mike. And that question is essentially, what must change about the community for it to remain vibrant? So we'd love your thoughts on that.
So Mike, you want to start?
Sure. Shannon, I think I'd like to complain to the community that we are not innovative enough. There is really, this is my sincere feeling, there is shortage of good ideas. There is not shortage of funding. I think even Mumi may agree with me, we need to get out of our comfort zone. We need to get out of what is really needed versus what we would like to do. We very much like, speaking from academia in particular, we very much like to work on a well-defined problem that I could do small scale, I could put it under microscope, cameras, take very nice visualization, publish, get a lot of citations. But you also have to raise the question, can I team up and have somebody do the applied side of it so that at the end, I can see this thing appear somewhere, because it's a pretty global economy. So thermal management, I can see so many opportunities that are not tackled. Again, difficult problems. The HVAC problem that I mentioned, and I said 1/3 the weight and 1/2 the size. Where did that come from? Well, run it. I agree, it cannot be evaporation as before. It cannot be condensation as before. But there is tremendous opportunity to shift from boiling to thin film evaporation through membranes and so forth. Work with drops of refrigerant instead of tons and pounds of refrigerant. So I think we need to really take time, either through sabbaticals or through time offs, to think how we can define something that is high impact, bring fundamentals of practical significance, and at the end have team members that can put it together. Thank you.
Yeah, I completely agree. I think Mike used this line. I was thinking about you kind of outside your comfort zone. You you have to really always consistently learn and talk to your collaborators. And so, for example, I think participating in this type of workshop, and NSF has a lot of those Dear Colleague letters soliciting new ideas. For example, we're just talking about emerging frontier research innovation. I look at the title that's submitted from the community. Actually, there was a Dear Colleague letter sent to us available in November. We don't have a lot of thermal or related topics submitted from the community. For example, AI, right? So how we can use this new technology and to look at our fundamental science problems and have a completely new perspective. Those are very important issues and opportunities. I think I would like to challenge the community. So like Mike's side, they're like bubbles and a lot of fundamental study for example, I was also sitting in the future manufacturing panels, and I look at, there are a lot of opportunities this community can participate, but we're not playing a key role there. So we miss a lot of opportunities.
Hey, this is Ravi here. Can I add my thoughts, if you don't mind? This is
actually Ravi. Why don't you toss your name into the chat window, right? And then I'll let you ask your question up next. How about that? Okay.
What do you want me to do?
Just type your name in the chat window, and we'll have you be the first person on deck to ask a question.
Okay.
Great, cool. All right, would anyone else from the panel like to comment on the vibrancy of the community before we jump to the next question? All right, so going to that next question, this one is for Sven and Matt Bauer. The question here is, if you would shut down and stop funding this community, what would be lost? And similarly, if the community decided to stop applying to your agency, how would that affect your core mission? So Sven, do you want to go first?
Sure. Can I pick which one?
Sure, go for it.
Can you put the question back up?
Yeah, I'll just read you the question. How about if you would shut down and stop funding this community, what would be lost? And if this community decided to stop applying to your agency, how would that affect your core mission?
Yeah, so I'll take the latter one. So our core mission is, if you look at buildings, let's start with that. 40% of all energy use, buildings consume 40% of all energy use. I mean, that's bigger than like any other sector. It's bigger than the transportation sector. It's better than the industrial sector. 75% of all electricity is being consumed in buildings. 30 to 35% of all carbon emissions are attributed to buildings. It's a huge deal, and our office looks at all building technologies. Looking at envelope technologies, thermal storage technologies, like advanced lighting, sensors and controls, window technologies. We need ideas, and if folks weren't applying, we would be at a loss. We span the entire TRL level, and going from R&D all the way to integration and to codes, and ultimately how to lock in savings is through codes, but codes are based on available technologies, and you have to always improve on technologies to be able to increase and make codes tighter, and efficiency standards and whatnot. So if the innovation were to stop, and a lot of the innovation is based on university research and partnering with our national labs, that would be a significant impact to our core mission, and the mission is for the well-being of the United States.
Yep, the interdependency I think is very key. Matt, did you want to add anything to that?
I mean, I'd say this wouldn't be an interesting job to have if we did not have the thermal transport community feeding new ideas for our application. It would be redesigning things that engineers have tried time and time again and coming to the same optimization dead ends. Without new materials, without better understanding of how novel fluids and their interactions, we would not have a new tool belt to do anything different than what's been done for the last several decades. And that would not be a very satisfying technology to be in.
Thank you. Great. All right, Ravi, you're up. Would you like to pose a question to the panel, and then we have a question for Peter next?
I have a comment rather than a question to the panel. It goes back to the original question that was asked, that are we innovative enough? And I think Michael and Ying touched upon it. Let me say, I worked, as some of you know, that I worked in as well as now on the other side. I was one of the the last year, in December, there was one of the sessions was in thermal management. I believe Tim Fisher was one of the speakers. And Tim made his opening comment was that we are the garbage collector. Okay, I remember very clearly. Tim made the comment that we are the garbage collector. Okay, that tells you a lot. We want to be, as a thermal community, in the driver's seat, rather than in a situation where somebody is creating a problem that we have to just say that, okay, I'll figure out something so that you can still continue doing your own technology development. Okay, particularly in the context of energy. Okay, energy and climate change. I just cannot imagine. I mean, the thermal science plays such a big role.
Yep.
All your industrial systems are heat-based. No matter you electrify all the buildings, you can electrify everything that you want. At the end of the day, in the buildings, you still need heating and cooling for comfort. Okay. So I really think that we as a community can be much more of a driver's seat rather than always following. Okay. And that is, I would say that I will urge the community to go. And particularly when you talk about climate change, and that's why I put one slide that we don't have the luxury. We have only 20 years. Okay. So I would say that it behooves on us as a community, look at the problem, say, here's the time horizon, this is what needs to be done, and map it back to the fundamental science that is needed to solve and accelerate that development, right? And that will really enable us to be in the driver's seat. That's one. Second thing is that I would also say that one sole inventor or researcher cannot solve these big problems, okay? So teaming is going to be very, very critical too. Teaming means that when you go and talk to a material scientist or a computer scientist, your game better be equal at that level, right? So that they get very excited about your vision and they say, okay, I want to participate with you. I want you to lead this project, but I will be helping you in your.
Yep.
That is
very good comment, Ravi. We should have had you on this panel from your past program manager days. But given the sake of time, I kind of want to pose one question to Peter here. Let me share my screen. Right. So Peter, this is kind of a hard question. The question we have is essentially, why should this community keep applying to your agency when there are other opportunities?
Well, I don't think it's a hard question at all, because if you look at every agency, they all have their unique roles. NSF, ARPA-E, as well as the Buildings Office, they all have different roles, and ARPA-E really looks at those disruptive innovations. And I think Ravi made some excellent comments that, you bring together teams that would have not worked together. As an ARPA-E agency, you do not have the budget of all the tech multinationals together, but yet we can have impact because we can stimulate new thinking. I can put a biologist next to a thermal scientist, next to a material scientist, and let them solve a problem in a different way. And that is, I think, going to lead to the innovations that we need. And I think Ravi said it right too. When I worked in my prior industry, I always said, nobody cares about the temperature of your computer chip. It's not on the box, right? The only people that will care about the temperature is somebody who builds refrigerators. Everybody else cares about performance, size, reliability. So as a community, we need to learn to express our great sciences, because thermal management is critical to everything in the metrics that matter. So that requires us to go out of our box, to fall on our face and learn and learn and learn. And at some point we can express, hey, if you do transportation, this thermal technology could make this much more efficient, can reduce this much more emissions. And that is just the challenge and opportunity in front of us. And I think the agencies that we have, the great people on this panel and agencies that like Ravi works in, can help us build that framework, but we also need your input to build this together.
Got it. Yeah, just to push back a little bit on that, Mike mentioned that at the beginning, we don't really have a shortage of funding. I think that's definitely true, especially with, essentially the breakthrough energy ecosystem coming into play. But why should people keep applying to federal agencies when there are all these other opportunities out there? What's unique about federal agencies?
So a federal agency can give you a lot more connections. If you go down an industry path, and I know that path very well, you're locked down into one solution and you'll never have the impact that a federal agency can offer. Plus you get teamed up with an enormous great set of other scientists. I've worked on programs with ARPA-E and with DARPA, where all the competing teams really become friends, And still those relationships last for decades. So the career boost I got from working with those advanced research agency is unparalleled. What I would have gotten out of a single stovepipe patented approach with another private investor. So I think there is an enormous opportunity for young engineers and for people with bright ideas to work with our agencies.
Great. We also have a question here from the audience. Terry Hendricks, would you like to make a question?
I have to drop off.
Yeah.
All right, thanks, Peter.
I would like, it's not so much a question, Shannon, but I'd like to make a comment here.
Can you keep it short?
Yeah. I agree with what's being said here with regard to thermal systems and thermal technologies, and the whole discipline has to be able to learn to deal across multidisciplinary lines to have the impact that it should be having. Everybody's made the point, and they're correct. Thermal systems pretty much drive everything, but you have to be able to relate thermal performance back to the key metrics that are important to any particular system design and any commercialization effort.
Great, thank you, Terry. All right, I think we have time for one last question. This is actually going to be a two-part question, and I'd love for anyone in the panel to share. The question here is, if your program funding increased by 2x, what would you do differently? And if your program's funding increased by 10x, what would you do differently? So initially we were planning on asking Matt and Sven to answer this one, but I'll kind of open it up to anyone in the panel. It's kind of a hard question when you think about just those two scales. So 2x and 10x.
So I'd like to comment, Shannon. I think what I will do is to change the impression out there. I'd like to quote something from Earl Nightingale. We become what we think about. So if Tim Fisher thinks that we are garbage collectors, we will stay garbage collectors. And on the other hand, we charge ourselves to tackle problems, as Terry just mentioned, that are fundamentally impressive, exciting to work on, but at the same time, we need to find ways to get them to practice. Why government agency funding? Because you de-risk. You work on earlier stages, breakthrough energy and others would value this. So it really use it as de-risk because government funds the projects that industry may not fund on their own. So I think money helps great deal. There are many problems we would like to define, but the energy would have to come from the proposals. The typical program director cannot come up with new ideas and do it. That's not the charge they have. The charge they have is to take ideas from you and to develop them. Thank you.
Yeah, if I get more money, I think two things I would do. First of all, is to fund more high risk ideas that may or may not work. High risk, high reward type of ideas, early stage ideas, like Mike pointed out. Government and especially NSF should do that to see ideas probably will be successful or lead the way, and 20 years later. And also the other thing is really truly interdisciplinary initiative. For example, climate change. There are many issues, and or wildfire, all related to many different disciplines of that we can thermal engineers should be able to contribute. Thank you.
I would add that I echo those comments. I mean, you can take some more liberties of what types of projects and areas you can fund. With the higher risk, higher reward projects as well. With this new incoming administration, we're expecting that there's going to be an emphasis more on demonstrations and deployment and market transformation issues or activities. If we had additional funding, we could spread that around more and actually accelerate meeting those objectives while not taking our foot off the pedal on looking at new, high risk, high reward types of projects. I think with even at more funding, you can spread that risk, right? You can. There might be like if we might only be able to fund like one project in a given area that it might be really high risk. But if we have additional funding, you can take multiple shots at an opportunity and fund multiple approaches trying to achieve the same outcome, but in different ways. So that's what I would add.
Great. All right. I have one question here that came as a kind of a direct message. Let me actually open it up for that individual to ask this last question. This is Debyoti Banerjee. Would you like to unmute your microphone and ask your question?
Hi, can you all hear me okay?
Yep.
So I think there was a comment in the panel that said that, there is people are looking out for good ideas, and then there is a lack of good ideas from the community. So I'm interested in knowing the definition of a good idea, what the constituents of a good idea, and how do funding agencies separate science fiction from a good idea?
I can quickly comment before I have to drop off for another meeting. The excellent point you raised, DBG. To me, a good idea is the idea that is fundamentally exciting. It's something that is a concept that needs to be proven, but at the same time, it has practical significance because we do need to create jobs, we need to create economic activity, and we cannot just all of the projects be focused on the fundamental science only. So a good idea would be the one that multidisciplinary brings it together, drives it home. Thank you.
Yeah, just my comments also. Actually, internally, we did an access of how we can find a better identify outliers. So I actually went through all this database back to 1970s and how we can detect early stage ideas that are kind of good ideas. And for example, Aruma Janda in early 1990s proposed this nanoscale basically photon transport study, and it went through a very difficult time at the beginning because nobody believed this, right? So I guess and then it was supported by Eager project or Sugar project at the time. So I think I think it's a tough call. I mean, we have to. So I think for the program manager, we have to really, develop our own taste and study, continuous improve ourselves. And and also always talking to the community. If I'm not sure about something really new I have never seen, I usually, get some ad hoc comments from the community. The very, very good comments. It's difficult, it's challenging, yes.
Great.
Thank you. I'm going to step in and because we're running out of time, and I just wanted to thank everyone for participating in the panel.
Okay, folks, welcome back. This is the final session of the workshop. Reports from moderators and final discussions. Each group of moderators will present for about 10 minutes, and we'll go by the order of the days. We'll start with reports from the AI group, then we'll move on to thermal management, then health, manufacturing, energy, and finally a short presentation from the program manager panel. We'll start with AI moderators.
Hi, Yov. I just want to add, can you hear me?
We can hear you, yes.
Yeah. So after the presentations, the audience, you can ask questions. So the moderators and the panelists who are joining for this session can help answer your questions. That will be about 40 minutes or so. Yeah, thank you.
So the AI moderators.
Okay, I'm here. So I will share my screen. Just a minute. So can you see my slide?
Yes.
And yes.
Okay, great. Yeah, I will start. So everyone, on our first day of the workshop, we had 5 panelists sharing us with their own research, particularly their research that is related to our topic of AI, quantum computing, and data science of the first day of workshop. We also had a full 1-hour question and answer session to know our panelists' vision of the future of these new technologies and how we heat transfer community can benefit from or contribute to these areas. So we have divided the information acquired from the first day into 2 categories. First is regarding how our thermal transport research can benefit from those emerging areas of AI, quantum computing, and data science. While the second category is about how we can use our knowledge in thermal transport to help improve and advance those computer science areas. So regarding the first category, the first thing we want to mention is that the first application of AI and data science, so on which we already seen on an increasing number of publications, it is the design of complex or new materials for thermoelectric and other thermal applications. So, and also the design and prediction of various defects in materials that could affect or help us improve the performance of thermoelectric or other thermal materials. They can also be greatly helped by AI and data science. And the second thing is that AI and data science can also help us better understand the complex physics associated with thermal transport processes. For example, when there are multiple types of lattice vibrations, we call it phonons, involved in a complex material, or when we have to deal with the interaction or coupling or the concurrent transport of several different heat carriers like electrons, phonons, and magnons. So data science can greatly help us in understanding those complex physics. And the third topic, as discussed by our several of our panelists, is that AI and data science can directly help us accelerate or automate the prediction of thermal properties. So as you can see, there have been like many publications emerging on applying either machine learning or big data to predict the thermal conductivity, thermal boundary conductance of materials. They can also help the creation of mapping from thermal cameras, or a very important aspect is that machine learning based potential provides us with a unique opportunity to improve the accuracy of atomistic modeling of thermal transport in materials. Other than that, AI can help accelerate computational thermal fluid simulations and system identification and the discovery of various heat transfer physics. The fourth point we want to make, as pointed out by Payman, is that quantum computing, it could provide us with a unique tool to really solve complex and large quantum or classical problems using quantum algorithms and quantum computers or simulators, so which are currently maybe too challenging to solve with our current methods. So that's about the first category. And the second category is regarding how we, thermal transport community, using our knowledge and expertise to advance quantum computing and the development of quantum devices. So as pointed by Austin, we could understand the noise mechanism that's associated with lattice vibrations of photons and also hot electrons. So in those quantum devices, and help develop strategies to reduce noise and thus improve the performance of quantum devices. That's one important aspect. And also the other thing is that quantum devices, they typically need to work or operate under extreme conditions like very low temperatures. So thermal management, it definitely is a very important aspect of research in that area. So I will now handle this to Matteo to discuss the visions we obtained from the question and answer sessions.
Thank you, Ian. Do you mind to go to the next slide, please? Okay. So we had an interesting discussion during the second hour of the meeting, and it was about essentially setting the basis for the vision on the role of artificial intelligence and possibly quantum computing in thermal transport research. And well, what emerged quite clearly is the opportunity to use artificial intelligence, if not actually the necessity to use artificial intelligence to solve problems that are beyond say the current possibility for the man intelligence to be described in an analytical closed form. And there are definitely plenty of examples in thermal science, one of which was also discussed in the presentation of Simon and Jeff. But the idea is that fundamentally AI can help in all those situations where a clear analytical description of phenomena is out of reach, or it's visibly different from what we measure, or anyway, for all those phenomena that are ill-posed or are governed from some kind of inverse problem descriptions. AI can also be useful in problems where the physical formulation is known. In that case, it's very, the promising idea is the physics-informed machine learning optimization, which was brought up by several of our speakers. Now, going from a vision to the short-term mission, what we can expect practically from AI and quantum computing within the 5 years to come. If you can go to the next slide, thank you. So probably slide number 6. So the idea with artificial intelligence is that there are several outstanding but well-framed problems, like the problem of thermal properties in materials, that could be solved within the next 5 years. One of the major issues in this path is the availability of data for the development of these methodologies. And this is both in terms of quantity and quality of the data. And the reason being that most of the data used as we start growing this sub-area are obtained were obtained in the past and not with the essentially insight necessary to use them today, to leverage them today to perform machine learning investigation. So there's a real need to think about how to integrate experimentation and machine learning in the future. And in the short term, one possible solution to this problem is a technique using a reduced data set or sparse data set, and also, and importantly, use high fidelity simulation that predict certain phenomena from first principles. And this is also a very, very interesting area where it was mentioned that this high fidelity simulation could be even used to actually learn differential equations from the physical principles. And one area that is certainly very promising and growing fast, if not in thermal transport, at least in chemical engineering, is the area of smart experimentation. So we have experiments that can learn on the fly as we run, and that allow adjusting operating conditions in order to improve the learning rate and essentially minimize the number of experiments that one needs to run, which is definitely beneficial. So as far as quantum computing, if you can go to the next slide, Jan, there are definitely bad news in the sense that it's difficult to imagine that within 5 years we will have quantum computers. That's probably not going to happen, not even in 10 years. And although things are moving fast, it's reasonable that the first application will happen in the 2030 decade, at least in a demonstration type of problems. And the point is that the real importance of quantum computing comes when quantum computers will be able to solve problems that cannot be solved otherwise by traditional computing techniques. But even though, say, from the hardware point of view, there's still a long way to go, there are many aspects of quantum computing related to quantum algorithms and simulators that can benefit, say, that can actually, from which the say traditional computing can take advantage. Now, to go back to the original point raised by Jan, please go to slide number 8. When we think about machine learning, if we ask the community, I'm sure we will have a quite diverse set of responses, in the sense that there are always people that are optimistic about the use of machine learning in thermal transport, some other people that are more skeptical. This is an important topic of discussion. Well, something that emerged from the conversation we had with the panelists and the audience is that, well, the idea is that inventions cannot be disinvented, that it's normal for people to start using AI for simple problems, maybe not in the most efficient way, but that's somehow a necessary step for the thermal transport community to grow and learn how to take advantage of this technique as much as possible. And it is somehow the first step necessary to reach the level of quality of innovation that maybe it's already available in other fields of science, like image analysis. And say that the conclusion is that in this effort, in this path, it is vital that thermal transport community does not close itself, but but open up and work directly with the computer science and machine learning community. So one very direct comment that came from multiple panelists is that somehow research projects in this area should always combine experts in thermal transport and experts in advanced computing and machine learning for them to succeed and really give the real innovation in the field. And this obviously can be beneficial also for education purpose. And to conclude, I will also mention an interesting idea, which is the one of the grand challenges. It would be a working mode that we could mimic is the one used for the image analysis science that created the grand challenge problems. And one of these is the ImageNet in 2012. So the idea could be to select a few outstanding problems and build a framework to work on this problem as a community. And with this, I will stop. Thank you very much.
Thank you very much. The next group of moderators is thermal management. Justin?
Yeah, can you hear me? It says hold on, let me try to share.
Yeah, we can hear you well.
Excellent, thanks. And all right. So this is Justin Weibel here at Purdue. And so I'm going to kind of present, but my co-moderators, Demena and Sharjah, are on the line as well, from what we discussed in some of the discussions in the breakout sessions that we had. And I thought I would go through this and first just summarize, in case everyone wasn't there on the day of this panel, of what our panel was about and who spoke. So we had this distinguished set of panelists, Sam Graham from Georgia Tech, Mark Spector from ONR, Ajit from AFRL, Evelyn Wang from MIT, Tim Fisher from UCLA, and Samantha from Illinois Tech. And so we had this diverse kind of set of topics, and thermal management is very broad. But so each of these speakers presented for about 10 minutes on a given topic. And in addition to their presentation, we really asked them if they could distill their talk into 3 key challenges or grand challenges they thought were facing the community in terms of their perspective on it. So for example, right? Sam was really focusing on the future of electronics and how thermal management is needed there, and had identified these challenges related to thermal materials, right? Electrothermal device modeling, and how to leverage advanced additive manufacturing techniques into them. And so in these slides here, and we know this is being recorded, we did want to give you kind of their original inputs to the discussion that kind of led to the framework on how we interpreted it. And so going through the others perhaps more quickly, just to give everyone a sense, right? Mark gave a talk on the perspective of O&R on thermal management, which gave this broad perspective on many different areas, and he listed out, right, their mission, but kind of distilled it down into focusing on two-phase systems and how to push them, right, to high vapor qualities and large systems, as well as how to leverage additive manufacturing techniques again in those systems. Dr. Roy was really more focused in his case on innovation and thermal materials. And so his challenges for the community were how we could develop, or I'll say accelerate materials innovation with design tools such that they could have kind of applications to some of these extreme environments, which there's not material solutions available, and also to be more multifunctional in their characteristics. And going on, Evelyn summarized a lot of the community efforts surrounded on understanding just the fundamentals of evaporation up to the boiling process, and some of the device development and how we're starting to bridge the gap between this fundamental understanding and developing solutions, and identified gaps both from that fundamental perspective, but also into, again, how to do this and implement those in a scalable way. Tim's challenges in his talk were really thinking about practicing across scales and focusing in particular that the thermal management community may have not to date focused enough on understanding and exploiting kind of this temporal time scale. So how to exploit non-equilibrium transport to your advantage, how to take advantage of transients in thermal management components because they'll just be necessary. Design for steady state is far past us. And then lastly, the topic and the focus was really on thermal management of turbines from Sumanta, but then a lot of his challenges were focused on how the thermal management community, and really talking to the last topic on really machine learning and how to leverage information from those data sets. So as the moderators, then we took all of those challenges, and this is again a lot of text here, but we wanted to share the inputs to the panel, and breakouts were a consolidated set of these grand challenges, at least from what our panelists had identified. And we'll go through these more in the coming slides, so I won't try to discuss each one. And the objective of the breakouts, then, we split into 5 different groups. And each of these groups were picked, I'll say as many as they wanted, but we encouraged picking a couple of priority challenges that they wanted to discuss. And the idea here would be a bit of natural selection as the most pressing and of most interest issues to the groups, and that particular panelist leading that would identify kind of these pressing issues. And I know this is Professor Wang's group, they formally voted amongst the community and decided which 2 they would talk about. And so once these were identified, we had it set up so each of the rooms had a Google Sheet to record their ideas. Special thanks, we volunteered note takers on the fly, and they were willing to record in each of those rooms, not just the challenges, but then what does our community need to be doing in terms of a research prioritization to actually solve those problems. And then, the moderators, Dimena and Xiaojian and I went back through all of these worksheets, listened to those breakout sessions after the fact, and tried to kind of consolidate, and we'll present now some of those thoughts. And here I'm then showing the grand challenges that were ultimately discussed. And so you can see there was a bit of a down selection. We had 9 before, now we have 7, and also a little bit of regrouping in terms of where the solutions that were being suggested kind of mapped to some of the same challenges. And so we kind of have narrowed it down to 5 key challenges that the community had identified, right, grouped here, and these are just retaining some of the initial numbers related to materials innovation. So this is thinking, really using validated, how do we validate our, right, multi-scale materials design tool to accelerate innovation? And similarly, not just electrothermal model, but generally advanced multi-physics thermal models that will facilitate co-design for thermal management as opposed to having purely thermal functions. And so that was one area. The lack of materials that can be integrated into devices for some of these, I'll call them extreme applications, hypersonics, directed energy, and some electronic systems are really in need of thermal materials innovation as well. This machine learning topic, which we'll talk about and has been expanded. Two-phase thermal solutions was discussed quite a bit, and really how to advance that understanding and have physics-guided solutions for it. And then lastly, I'll say advanced manufacturing, but also combine that in with scalable manufacturing techniques. So these were the topics that were identified, and in the perspectives that we'll provide, we'll really organize it around this. So the following slides are really then, these are those challenges that were identified, but talking about the solutions we wanted, the community wanted to pursue. These slides have a lot of text. I'm forewarning you when I'm clicking to them. My goal is not to discuss each one of these points, but just knowing it was recorded, we wanted to share kind of without filtering all of these different priorities and thoughts that were discussed in the panels themselves. I'll give kind of a quick paraphrased piece on each of this, on each one of these. But in short, on this materials innovation, there's really a need to think about uncertainty quantification was a major topic of discussion. So having metrology that has quantified uncertainty, and then being able to propagate that uncertainty in some of these materials models that we have is critical. And just the acknowledgement that developing and maintaining codes connected with large material database is a major undertaking, and this will need large group efforts to do those, similar to what NIST has done for materials and chemical processing or chemical properties. So that was one. On this, I won't go through all of these, but again, in the emerging applications in hypersonics and directed energy, there's new thermal functions that these materials need to have, both in terms of extreme temperatures, thermal conductivities potentially that are have on-off ratios are varying, different even transistor materials, underfill materials in thermal packages, a lot of materials kind of challenges categorized here. And then in integrations, just the heat sink solutions, then we talk about thermal materials perhaps separate from the thermal management solutions, but basically as the heat transfer solutions or the heat sinks becoming closer and closer, the dissipation mechanism is the material itself, and that's more of a mutual interface. I won't talk about machine learning. I know we're short on time, but there's a lot of things here, and we discussed that. There's a little bit of overlap with the previous panel that we'll want to think about. On two-phase heat transfer, it's really about understanding the root resistances and pushing these things to controlled high vapor quality systems, whether that be evaporation or controlled boiling. That's what we need. And then in additive manufacturing, there's quite a bit here.
2 more minutes.
Yep, I'm pretty much done now. I don't want to go through additive manufacturing because there's quite a bit here, but I would leave it. So what's next in terms of from our moderators? So I think we all know and understand. I want you to be aware that we'll prepare a summary paper kind of describing these challenges and some of the key research directions that were identified. But we kind of also acknowledge that everyone here and maybe all of the participants didn't get to participate in every breakout session and discuss every topic. So we have created what will be kind of a living Google document or a Google sheet where, and if Demena, if you could even post this as in a link to the chat here, where we do want you to continue to put any other challenges or priorities or things you were missed and you didn't see in the list here or don't see if you go and look at it. And then also as we prepare the review article, I think an important piece will be, we don't want to kind of hand select examples of research that's addressing or aligned with these topics, but want to make it more democratic. So if anyone has of their own research or others, papers, studies, work that they think is really mapped to the challenges that we're facing. It's just in the sheet, there's a list. Just put a DOI number and put the challenges you think we're facing, and then we'll try to cite and get a representative cross-section of this, so we can kind of also give kind of a forward-looking vision on here's what we're currently doing and where we are successful. So I guess this is maybe the most important part. We'd love to keep everyone here engaged in the process as we prepare that. And so that's what we have and prepared from our group. Okay, Demena, Xiaojia, anything I missed, if you want to chime in?
I think that's good, Justin. Thank you.
Okay, the next group of moderators is on health, Fatima and Dion. By the way, Justin, if you want us to post the link on the website, on the workshop website, please let us know.
Okay, yeah, we'll definitely do that. That's a great idea. Thanks.
Okay, good afternoon, everyone. This is, my name is Dion Anthao. I was a moderator along with Fatima Hassanipur from UT Dallas on this panel 3, which was on health and sustainability. Like Justin pointed out just a few minutes back, as moderators and panelists, we will be writing a perspective paper at the end of this. And so if you have any suggestions for grand challenges that are not covered under here, or areas of research that are up and coming, or that the community should think about in the areas of health and sustainability, please feel free to contact Fatima or me at our email addresses listed here. Similar to the other reports that were done, this is an overview of our panelists for the health and sustainability session. We had Dr. Esther Beltran from the Florida Space Institute, Dr. Cynthia Hipwell from Texas A&M University, Dr. John Lehnhardt from the Massachusetts Institute of Technology, Dr. Howard Stone from Princeton University, Dr. John Bischoff from the University of Minnesota, and Dr. Mehmet Toner from Mass General Hospital. Now, while our session and our panel was on health and sustainability, we had very diverse set of talks. And so we've broken them down basically into 3 groupings. And the first is the thrust area of desalination, food, water nexus, and climate. And there's some overlap between the various sessions, but we'll cover that in the end. And the way we've outlined our report is talking about a bit about the state-of-the-art challenges that were addressed by our speaker, our panelist, and some of the opportunities for future work. And we'll start with this thrust area 1, which is desalination, the food, water nexus, and climate, that was addressed by Professor John Lehnhardt. As a lot of us know, RO is one of the most, if not the most efficient desalination option out there. But as a thermal community, if we want to talk about thermal desalination or distillation, in order for it to be competitive, you're talking about achieving efficiencies or this gained output ratio of GOR on the order of about 20. And so that means we've got to increase the energy and exergetic efficiencies in these thermal distillation processes. Fouling and scaling is a major issue that occurs in these thermal distillation processes, especially on these metal heat exchanger, expensive metal heat exchanger components, which tends to increase the cost of the systems. A method that exists within this thermal sphere, that's membrane distillation, which is the next step in terms of, as compared to some of these multi-effect or multi-stage flash processes, is cheaper, and it can use components such as cheaper low surface energy membranes, which offers new opportunities. And in terms of the opportunities, we've broken this down for this thrust area into 3 different areas. For desalination, the opportunities lie in high salinity feeds with solute recovery. A key area is using produced water to recover both the water from it, as well as some of these more important constituents like lithium or rare earth elements. High fouling feeds with scale control. Here we're talking about materials development, So materials that are both low surface energy and high thermal conductivity, as they will be used in the heat exchanger components. Low capital expenditure systems. Again, this is talking about systems that can use cheaper components. So metal is typically an expensive component in the heat exchanger. And so using cheaper polymer, high thermal conductivity polymers could move us towards low CapEx and OpEx systems. System level engineering and optimization, and water recovery for agriculture needs. In the area of food, the opportunities lie in developing cheap, in both in terms of the cost of the technology as well as its OpEx or energy usage, cheap cooling technologies for food preservation, and of course, keeping in mind the climate impacts of the food process or the food cycle, especially fertilizer production, and developing novel methods for ammonia production. For example, ammonia is typically produced from a lot of fossil with a lot of fossil fuel input, and so developing cleaner, novel methods for ammonia production, as well as distributed and more localized fertilizer production. So using raw materials and developing fertilizers at the place at which it will be used, so the farms where it will be used. And finally, as Dr. Lena had pointed out, the climate situation that we are in at the moment is a heat transfer problem. It's a complex heat transfer problem with a lot of different multi-purpose inputs or multiple areas of expertise that are required, but at its heart, it's a heat transfer problem. And so modeling the Earth's energy balance is a huge opportunity here moving forward, as well as talking about control of the environment via geoengineering. And these are opportunities. This area of climate is an opportunity for convergent research, right? Using researchers from a variety of different fields, not just in engineering or thermal transport. The next thrust area was in the area of materials for health. We had two speakers here, Dr. Cynthia Hipwell and Dr. Esther Beltran. Dr. Hipwell spoke about the frontiers of transport for touch, so talking about haptics for the future. The context here is to enhance the feedback in any haptics interface. So talking about human machine interfaces, enhanced virtual reality, and prosthetics and virtual human reactions. So the pandemic that we find ourselves in, which has reduced interactions between family members and friends. So this concept of remote touch is what's currently motivating a lot of our challenges and opportunities, among other aspects. The challenges lie in the haptic device operation and increased realism of the haptics. In terms of the operation, we're talking about developing miniaturized active materials for rapid switching, innovations in thermal response, as well as flexible electronics thermal management. So dissipation of heat or thermal energy in epidermal electronics, and then transport for varying skin, transport in these electronics, thermal transport under varying skin conditions. And of course, to increase realism, if you ever want to have these thermal displays, as Dr. Hipwell spoke about in the future, developing tunable thermal properties in these materials that are used for these haptic interfaces. I believe my colleague Fatima will talk about the other three presentations.
Hello, everyone. I'm Fatima Sanipur from UT Dallas, and I was a moderator of the breakout session, having Dr. Beltran, Dr. Bischoff, and Dr. Stone. And as my colleague Dion mentioned, this is a summary of what we had in the panel discussion and in the breakout sessions. So the next speaker was Dr. Beltran, and she talked about the human health in space exploration. She started her talk by emphasizing that thermal radiation and the radiation that astronauts are exposed to in the space are the highest risk that they are having. So there are lots of opportunities for thermal transport communities And what she mentioned was that they need lightweight and innovative materials to tackle this challenge. So a summary of the challenges and opportunities as listed here are the real-time radiation monitoring, advanced lightweight, comfortable, and flexible materials for radiation protection of key human body parts, head and heart, and thermal regulation of astronauts during extreme temperature cycling. She also talked about the graphene nanocomposite and the collaboration that she and her group have, they have with several universities. And she talked about the promising application of this graphene nanocomposite in this application. Dion, can you do the next slide, please? Yes, thank you so much. And the next talk, yes, the next talk was by Dr. Bishop and Dr. Mehmet. They are the Director of Engineering Research Center for Advanced Technologies for the Preservation of Biological Systems. They started their talk by the benefits to the society and the research that they do in this center. But the specific goal of this center for the next 5 to 10 years are developing technologies to advance transport, shipment, storage, and banking of biological systems. And Dr. Bishop mentioned that biopreservation from an engineering point of view include 3 components of temperature, pressure, and concentration. And a summary of the challenges and opportunities outlined by Dr. Bishop during the panel and the breakout sessions are outlined here. So these challenges include excessive ice formation, the CPA toxicity, thermal and mechanical stress. One of the challenges that they're facing too is the moving from lab to the technology, scaling technology from animal to human, scaling of nanoparticles, the environmental issues, and the ethical issues. And the next talk was by Dr. Howard. His talk was about the fluid dynamics of speech, mechanism underlying pathogen transmission. So Dr. Howard discussed the research that they do in their lab using experimentation, simulation, and modeling for virus transmission to investigate the role of social distance and contact time during local interactions and exposure to virus. And since virus may spread by individuals without symptoms, so without coughing or sneezing, so the fluid dynamic of speech and the related vortex formation during normal talking is one of the things that is very important to study. And Dr. Stone also elaborated the challenges and opportunities that our community can help with. So these challenges are listed here: the integration of transport phenomena with public health, real-time ventilation, CFD and information sciences, rheology and drop formation in speech, visualization of the flow-driven transport process, impact of microclimates in humidity and temperature on the droplet trajectory, and the effect of filtrations and materials of mass of flows and mixing with the ambient.
Thank you, Fatima. Just before we wrap up, some cross-cutting opportunities and factors that'll affect us moving forward in terms, and what we need to keep in mind in these areas of health and sustainability are the role of artificial intelligence. I won't talk about this much because we've had an entire session on this, but some areas that could be important are identifying plant genomes, where these genomes are resistant to abiotic stresses, and especially training of the next generation of students in AI methods. The second aspect that was stressed across the board was to encourage stakeholder participation, which is extremely important in these areas of health and sustainability, where we have a lot of societal impact in very cross-disciplinary issues. And so involving stakeholders in the design and implementation phases will enable a higher success of adoption, as well as the IP and technology transition to industry and leveraging industry to provide us with feedback to enable a smooth transition for the eventual end users. These were factors to keep in mind and opportunities for future work. With that, we want to thank you. And once again, if you have any feedback for us, please send us an email. It's on the email addresses will be on the website too, I believe. So thank you.
Thank you, Leon and Fatima. The next group is manufacturing, Ed and Sanya.
All right, I'll go ahead and start. All right, so our panel that we moderated, the topic was manufacturing. The speakers on the panel focused primarily on additive manufacturing. There was a lot of discussion of additive manufacturing because it is a frontier in relationship to thermal management devices and thermal transport. So I moderated this panel along with Ed Kinzel, who will take over in the midst of our reporting back. So I'll handle the beginning of it. So our panelists were Karen Thole, Yan Shen, Kirk Rogers, Michael Ahadi, and Bill Olbricht. We got the academic perspective on the frontiers in particularly laser additive manufacturing from Professor Thole and Professor Shen. We've got really good industry perspective from Kirk Rogers. And then we got perspective on the intersection of manufacturing and thermal transport in funded programs from Drs. Ahadi and Olbricht. So the themes that the panelists spoke about, we took a little bit of a different approach in that we synthesized across all of the panelists in our reporting out, and that's how we'll report out. The main themes that the panelists presented on in terms of their research and programs were laser additive manufacturing frontiers, computational modeling of laser additive manufacturing, thermal devices made with additive manufacturing across multiple additive manufacturing techniques, what the different additive manufacturing techniques are, the characteristics of those techniques and applications that are addressed using devices made with those additive manufacturing different techniques, and the intersection of manufacturing and thermal transport in funded programs. We gave 2 guiding questions to the panelists as well as to the breakout sessions, to guide the breakout sessions. The first was, how does additive manufacturing facilitate new thermal transport applications? And the second is, what thermal transport knowledge is required or missing to advance additive manufacturing? And what I would encourage folks to do is, if you have additional thoughts that you didn't get to either communicate during the breakout sessions or you weren't able to participate in the breakout sessions, feel free to use the chat in this session to communicate some of your ideas with respect to these guiding questions or anything else related to manufacturing, and we'll capture that in the reporting for the report of the workshop. Additionally, feel free to contact us, and so we'll put up our email addresses again at the end. So we synthesized across all the breakout discussion sessions as well as the panel presentations to pull out what were identified as the current frontiers in manufacturing. And I apologize that it's written kind of in sentence form, and that's more for to be able to capture it in the reporting, but I'll go through these. So one of the first themes that came out in terms of the current frontier is that additive manufacturing has unique advantages in terms of providing improved performance for thermal devices. So for example, there's been demonstrations in improved power density and heat flux enhancement in thermal devices made with additive manufacturing. Additive manufacturing also provides reduced cost and design to production time. And that was a big emphasis that was made by multiple panelists. There are several options, both tools and techniques for additive manufacturing, techniques with multi-scale and multi-material manufacturing capability. And that, again, was emphasized across multiple panelists, that you get multiple scales and that there are multi-materials capabilities. We'll address that in some of the challenges as well. The relationships between process parameters and part quality are extensive. There are lots of different process parameters and they all impact part quality. And so this is an area of very active exploration. And so while there's active exploration, there's still a lot of unknown in this area. And many of the process parameters are thermal process parameters, particularly in laser additive manufacturing. Manufacturing process parameters impact the heat transfer performance. So there's a direct impact between manufacturing and the thermal performance of the part that's being made. The thermal history during processing impacts the microstructure of the part that's made, and thus the thermal history impacts the process structure property relationships of the material and parts that are fabricated. Financial investment in 3D printing and additive manufacturing is substantial and growing. So of investment in manufacturing, overwhelmingly, it's currently in additive manufacturing. Additive manufacturing of heat exchangers is already commercialized, and there are multiple companies focusing on this area. Heat conduction generative design is also commercialized. And so there were comments for those two bullets. There were comments about how industry has really taken the lead in terms of moving the frontier forward. And I think that's an area of further discussion of what is the role for research that is maybe earlier stage to intersect with the way that industry is really pushing the frontier in additive manufacturing. Computational prediction of microstructure and 3D phase fields is possible and has been demonstrated. And 3D printed structures with engineered porosity have been demonstrated, and that's relevant for the thermal applications for which additive manufacturing could be used. So I'm going to hand it over to Ed to cover the next two slides, but I'm going to advance the slides just to avoid it. So Ed, if you want to come off of mute.
Okay, so the panelists and in the breakout sessions identified several challenges. And so while for larger structures, the quality is there for particularly laser powder bed fusion, still going to smaller mesoscale type of features, it is challenging because of the surface roughness that affects things like the friction factor in heat exchangers. There are still issues with component repeatability for production. So if something is built in one build, doing that same process again on a different build with potentially different components on it remains a challenge. There are issues with still opportunities with multi-physics, multi-scale modeling, particularly around the melt pool. So there's been a lot of emergent work on simulating and modeling this, but that doesn't necessarily scale well as we want to predict for a part scale geometry. And in particular, as you get to the edges of the part, that starts to affect what's happening with that melt pool. And so there's a real need to do trade-offs with low fidelity modeling that can be run rapidly enough to make manufacturing decisions in the part. There are still challenges around the lack of validation and certification standards for AM, although those are potentially emerging from organizations like NIST. There are issues with high temperature and high pressures and these applications for materials that have been developed. This goes beyond general additive manufacturing, but is potentially still an issue with advanced additive manufacturing, and something that some of the materials that are processable with additive manufacturing can address. So things like strength and at high temperatures, creep, corrosion, and fatigue. There are real issues with joining dissimilar materials, both in terms of the fundamentals, in terms of CTE mismatch, but then for things like laser powder bed fusion, how do you integrate multiple materials into a single build? That doesn't exist for some of the other techniques, but for the commonly selective laser melting process, that still is a challenge. There's still issues in terms of part durability. How do these parts fatigue over long life cycles? And then in process, particular controlling the CTE for building up a large scale part. And so some of the needs and opportunities that were identified, I think several of the other sessions have identified opportunities around heat exchangers, particularly the opportunities that additive gives in terms of reducing the size and the mass of heat exchangers, but then going to materials that can survive high temperatures and high pressures, ultimately leading to high power densities. There are a lot of opportunities with using artificial intelligence and machine learning to enhance the modeling process, but particularly bridging between those high fidelity and low fidelity models. There are a lot of needs to, or a lot of possibilities to integrate instrumentation into AM parts. So including different sensors and actually incorporating those in the building process. There are opportunities and needs around education. And so broadening the workforce and the reaching out to more students, as well as broadening the participation in manufacturing and all of the ancillary supporting knowledge that needs to be generated in order to support that. There are needs for better in situ measurements during the processing, particularly kind of standardizing that. So many manufacturers have started to incorporate different in situ monitoring techniques. There's a number, wide variety that's provided or reported on in literature. Starting to standardize that so that decisions can be made across different platforms is important. That is something that extends to getting material sets, property sets for materials beyond high 6.4 and some of the commonly used things in aerospace. And so if we want to use more exotic materials or not even exotic materials, those material properties at high temperatures that are encountered during the selective laser melting process need to be generated. There's opportunities around predictive modeling, particularly the data fusion or the fusion between high fidelity and low fidelity models. There are needs to improve the accuracy. So being able to manufacture at smaller scales, being able to meet those high temperature and high pressure conditions. So durability at those high temperature and high pressure situations while maintaining the feature sizes that are benefiting. There's also opportunities to insert this into many different applications. So hybrid aviation, the next generation nuclear, stationary concentrated solar panel, lots of different things that were talked about in the other panels at the workshop. And there are still opportunities to explore the varied thermal properties that result in AM processed materials. So that can be things like varying the porosity in a print intelligently by doing the process parameters as opposed to a hierarchical geometry. There are still needs to identify scaling laws so that engineering decisions can be made for printing this, as well as multifunctional parts. So things that incorporate sensing, that incorporate different functions, a heat transfer and a structural function there. And then one last bullet point that
didn't make it in here. Beyond additive manufacturing, or beyond laser powder bed fusion, there are needs to do modeling for things like powder jet fusion, powder bed fusion. So things around the inkjet or the binder jet, as well as just the sintering process and understanding how that is affected by the part geometry, by the varying part materials associated with advanced manufacturing.
Okay, let's move now to the 5th session, energy. Zitang, Irina, and Karim, it's your turn.
Can you see my slide?
Yes, we can.
Okay, we're very happy to report what we have for the energy panel. We have 7 panelists. We break them into 3 groups. And so we are going to report what we have from each group in 3 core charts. So first, let's look at the nanotechnology for energy. The panelists are Professor Kang Chen and Professor Pramod Reddy. So for the state of art, what we have identified is we have significant progress in the fundamental understanding. For example, in conduction, we have seen the picture Gang showed. We have now touched the different pieces for heat conduction way beyond the traditional Fourier's law. And also we have made a tremendous progress in the near field radiation. If we can align our fundamental understanding with the practical applications, we could make a big impact in terms of radioactive cooling, thermal energy storage, no global warming fluids, energy water nexus, like harvest water from atmosphere, ultra low temperature control for quantum information, nano electronics cooling, and battery thermal management. In terms of the challenges, from computational side, we have been mainly using computational tools to predict properties like thermal conductivity. So can we go beyond property prediction? Can we kind of observe phenomenon? The challenges there are certainly involved with the computational cost and also lack of mesoscale tools. Most often, we also need to make proper assumptions to make those large computational work feasible. And also for the process modeling, for example, we still have a lot of challenges to model the, say, additive manufacturing process, the thermal transport process there. And experimental validation of models also has been identified as one challenge. That is related with this structure property relation. So when we talk about this structure property relation, oftentimes the challenge actually comes from the structure side. Like the challenge is to know the exact structure in the experimental measurement and to make the desired structures. And we have made a lot of progress in modeling solids, but modeling fluids has been very limited. MD can do some simulation, but certainly we are lacking of tools to properly model the properties of even pure fluids. And we need thermal devices to be implemented into energy systems to reduce the size and cost. And in terms of opportunities, we think modelers and experiments in our community should work closely with each other. And also we need to extend our collaboration, go beyond our community, like work closely with the material scientists or learn chemistries to synthesize the desired materials. And work with like process modelers to set the correct targets and work with other communities to co-design materials for multifunctionalities beyond thermal. And also explore far-flung equilibrium systems like transistors and plasmonic systems. With that, I will pass it to Irina.
Hello, I'm Irina Zenyuk. I'm associate professor in University of California, Irvine. And our breakout session featured 3 panelists. So Ravi Prasher, Sven Mumme, and Matthew Bauer. So it's quite a unique breakout session with two technology development managers from Department of Energy. So the focus was on thermal energy storage, and the state of art was nicely identified by Sven Mumme's presentation, and essentially also overviewed in ARPA-E Grids program, which funded most recently many awards, with $100 per kilowatt hour, and desired to have more than 5,000 cycles for grid energy storage. And this can be either thermal energy system or it can be electrochemical system with 80% round trip efficiency, resulting in $0.025 per kilowatt hour per cycle. So looking into lithium ion batteries, there's been recent boom because of Nobel Prize winners and because of significant advancement the field achieved in 30 years. It was interesting to see that for example, the panelist presenters on this comparing the thermal energy storage to battery energy storage, highlighting some of the advantages thermal energy storage, specifically higher round trip efficiency, lower cost compared to batteries, lower capital cost, and also lifetime and efficiency currently is higher. So there's a lot of potential in thermal energy storage for grid applications. In terms of, since we had quite diverse panel and quite diverse questions, we discussed in this breakout session everything from basics from fundamentals of material science all the way to the roles of NSF and DOE in funding this program. So we spent some time talking about concentrating solar power, or CSP, and this is the talk that Matt Bauer gave. Looking into this technology, it presents a lot of advantages because it can store energy over time periods of 10 hours and on really large scales. This is something where batteries are not great at. They're much better at short duration storage, but when it comes to seasonal storage, CSP or even hydrogen can present much better. Only the other endothermic processes can present a better solution. In terms of state of the art, in terms of CSP, the phase change materials, chlorides are already cheap and they're cheaper than nitrate salts. And the technology is cheap already compared to batteries. So, however, there's some challenges, and I'll discuss them in this quote chart, but high temperature corrosion is one of them. And for the phase change materials, they already are they already are quite sustainable and benign. If you look at a lot of battery materials, these organic electrolytes, these are materials that are scarce. You have lithium, you have cobalt that comes from mining in Africa. So there are a lot of potential for thermal energy storage. In terms of impact, what we can achieve, but using thermal energy storage for grid applications, for example, we can deploy more photovoltaic cells. We can use more wind because now we don't have to obey by the duck curve laws, but we can use off-peak electricity and store it now in this long duration storage. We can do seasonal storage and reduce overall peak electricity cost. And can also achieve grid leveling on daily storage, maybe with batteries and also with thermal energy storage. So key challenges we discussed, again, there have been broad discussion across many topics. So if you look into phase change materials, there is subcooling problems. So there's fundamentals that need to be addressed in this topic. Currently, there's no dedicated concentrated effort, and data is not well reported, so it's quite difficult to read through literature. Then the understanding the scale up. So whatever we learn in our laboratories, so using microliters of materials, scaling up to liters might not necessarily work, and fundamental phenomena we observe in this small quantities might not scale to the large quantities. So in terms of grid storage, there is a challenge of variability and future predictability. We don't have good models to predict what the grid will look like in future. So then how do we come up with solutions to accommodate that grid, right? Then seasonal storage is a challenge because you need something that can cycle twice per year, right? One for storage in winter, let's say, and one for deployment in summer. If it's, for example, in the United States, where wind is dominant, or California, where the solar is dominant, so we need to store in summer and deploy in winter. So so that's something. Seasonal storage is a challenge, and this is something maybe thermal energy storage can be helpful, because batteries cannot do that, and as I mentioned, hydrogen might. So challenge of high temperature corrosion of materials is a problem, as this operate at 700 degrees Celsius or higher. There is a lot of opportunities we identified, so the list is long. So for example, in terms of material solution fundamental science, phase change materials have a lot of potential and need still material discovery. So for example, eutactics and tritactics, combining those, this can be interesting opportunity. Using dynamically tunable thermal storage materials, where you can control not just melting temperature, but also conductivity. Then using material that can do both cold and heat storage. For example, looking at lithium-ion battery, can do both charge and discharge. So it serves as, if you think of batteries, serves both cold and heat, but currently this type of material is lacking. So in terms of phase change materials, encapsulation techniques, there is a lot of opportunities in that. Currently graphite is used, but surface area is still small, so maybe there's some options for polymeric approaches. One of the topics that we talked about was high temperature metrology, which is lacking. So sometimes it's developed in the lab, but not scaled up to the relevant technologies at scale. And this is really a big opportunity. We thought specifically also operando technology and measurements. So a lot of fields are moving towards looking at things that they evolve as, and something like advanced light source, so synchrotron X-ray sources can do a good job at observing materials that they melt or undergoing different thermal transformations. And also artificial intelligence will play a big role, we think, and specifically for material discovery, there's already projects like that. But also natural languages came up in discussion, and this is something, how do you read through the bulk literature we have across this many years, and how do you pick up the relevant information, how you sort it and how you present it. And actually we can learn a lot from already the vast majority of experiments that have been done, but we just don't know how to extract the data properly. So there have been large discussion about NSF versus DOE roles. NSF designed towards more of academia, PIs, and with the smaller budgets, DOE more like multidisciplinary, vertical integrated teams, and how can this both initiatives be leveraged to advance the field of thermal energy storage. And then one of the topics that DOE might be able to do is to create synchronized testing protocols for thermal energy storage and for material testing. This is something lithium-ion battery thrived in. We have synchronized protocols, how the battery should be tested, in which conditions. And this is something can be applied to thermal energy storage. Thank you. So the next we have Karim.
Okay, thank you, Irina. So our breakup session had Dr. Terry Hendricks and Dr. Peter DeBach, and it was a very interactive breakout where a lot of the topics were discussed. Here are some of the key points there. I'll keep it brief because I know we're way over schedule here. But the key points that were discussed in terms of state-of-the-art thermal barrier coatings, the resistance associated with it for turbines. Oh, I forgot to highlight that this is the aerospace and aviation breakout. So our focus primarily was on aerospace and aviation. So TBCs on turbine blades and how the resistance play a role and how we could actually use it for energy harvesting, and I'll talk about it in opportunities. Supercritical CO2 systems, that was brought up quite often as a state-of-the-art opportunity for thermal systems. Fuel reversing approaches, whether it being for aerospace applications or on Earth. Electrification of engines. There's currently engines that are 100% electrified, but it's not translating to aircrafts, and we'll talk about the challenges there. Thermal energy systems for lunar and Mars surfaces. I think this was also a topic that we talked about, and 3D material printing. And we also talked about Stirling versus thermoelectric systems as well. So the key challenges was, I think, using hydrogen as a fuel for aircrafts, primarily the storage issue. I think it's a there's potential for using hydrogen for aircraft engines. One being is, well, where do you generate that hydrogen as a main source? And then the other is storage, which is one of the bulletins there. Electrifications of aircraft engines was talked about as a key challenge, although it might seem like a major hurdle at the moment, but the same thing was seen. I believe Terry mentioned that back when he was at DOE, back in early 2000, where vehicles were considered electrification a major challenge, but now there are options where you can actually purchase electrified vehicles. So the same principle could happen for aircraft engines. Key challenges for lunar and Mars surfaces, which is dust impact on thermal systems, radiators. These are key things that need to be considered for challenges there. Fuel reversing and leveraging surface materials on some of these lunar Mars surfaces for fuel. There's limited materials that could be used for fuel reversing at these challenging environments. One of the key challenges as well for thermoelectric systems compared to Stirling was the lightweight for Stirling and lower temperature, and that made the advantage there better. Impact, obviously, higher efficiency systems, low impact on the environment, achieving the net zero carbon emissions in general. Opportunities, there's many opportunities that were discussed. One being energy harvesting through TBCs for turbine blades. I mean, we coat the turbine blades, but we're not taking advantage of that heat. Leveraging supercritical CO2, and another opportunity is sequestering CO2 from the atmosphere. I think that was brought up as a key point by Peter. Using CO2 for fuel production, I think that was another key point as an opportunity there, whether it's through chemical processes or thermochemical processes to produce fuel from CO2, leveraging hydrogen or other methods, or water breakdown. Hydrogen as a fuel for systems, I think that was seen as a big plus for aviation, and other opportunities for cryogenics for aircrafts, and Terry talked about that in his talk as well. Electrifications of aircrafts as evolving for automotive vehicles, I think that is seen as an opportunity there. There was talks about starting at a small scale and eventually progressing, which some of the smaller companies are doing that. Additive manufacturing, that was brought up as well. The challenge has been, and opportunities is essentially new materials for 3D printing, and can we develop new material for additive manufacturing, because the materials spectrum that we have right now is limited. But another caveat to that as an opportunity is through design of optimization of the manufacturing processes, can we overcome this material limit through thermal tailoring, essentially, of the manufacturing. So some kind of design optimization, I think this was seen as an opportunity there. And then leveraging programs like ARPA-E and NASA programs for some of these opportunities there. And with that, I'll pass it to you, Zeytin.
That's all we have. Thank you.
Okay.
Okay, so now the program manager panel, do you wish to, moderators, do you wish to give a short presentation, summary
Yes.
of the panel?
Yes, it's a very short one. We just had this panel about 2 hours ago, a little over. So I'll keep this very brief. We didn't have a breakout session, unlike the others. We just had a good conversation with a smaller group of our program managers that participated throughout the entire workshop. So just to remind people, the program managers on this panel were Dr. Michael Ohadi, Sven Mume, Peter DeBach, Matthew Bauer, and Ying Sun. After this kind of question and answer period, we got together and kind of had a chance to reflect on I guess what our takeaways were for kind of a key summary from the different viewpoints here. And there are kind of 4 bullet points that we took away. One, we felt that the panel had an opinion. We're not sure if this was a unanimous opinion, but it seemed like it was a pretty strong opinion that there seems to be a shortage of good ideas, not necessarily a shortage of funding. And that kind of led us to probe a little bit deeper. Why should the good ideas go to federal agencies was kind of one question. And the answer there was federal agencies can provide opportunities for teaming. They really have the opportunity to amplify impact. They can bridge different communities, and there will also be a legacy there for how things can interact, where other agencies or industries are kind of viewed as siloed, which I thought was kind of an interesting comment, because oftentimes I view some of the work in the government to be siloed. So very interesting there. We also learned that there are lots of opportunities for different funding mechanisms, as well as opportunities for people to go to DC, either as program directors, program managers, or fellows. So there seems like there's plenty of opportunities there. And then when we were trying to think of one big take-home message for the community, what we kind of came across is to kind of work on impactful problems. And it seems like a lot of the most pressing problems, the thermal community does have a very significant role to play, but that kind of, I guess, requires us to go in new directions and get outside of our comfort zones. So that was kind of our high-level reflections from the panel that we had earlier today.